Okay, now we shall see some more examples to see that how we can prove inequalities using mathematical induction. In our previous videos, we have discussed how to prove left hand side is equal to the right hand side to prove our claim using mathematical induction. So in this video, we'll talk about how we can prove the inequalities. So I will take one example and then we'll start from there. So the example that we want to see is we'll use the same steps that we have taken in our previous example. So example, it says that prove that what it is, 3 power n is greater than or equal to 1 plus 2n for all n greater than or equal to 0. So we are asked to prove this claim that 3 to the power of n is greater than or equal to 2 power 1 plus 2n wherever n is greater than or equal to 0. So how do we can prove this? So obviously we'll use the mathematical induction steps. So what we are going to do in our step number 1, again the same, let me say let p of n is going to be 3 power n greater than or equal to 1 plus 2n. Then in my step number 2, I will use the basis step. So step number 2 is my basis step where I'm going to prove this for the smallest value of n. So what is the smallest value of n here? It shows that it is true for n is greater than or equal to 0. That means I have to choose the smallest value of n, which is n is equal to 0. So if I can show that my basis step is true, then I can set up my induction hypothesis and then we can prove that induction hypothesis, right? So let's substitute the n is equal to 0 in the given claim, in the given equation, which is going to be 3 power 0 greater than or equal to 1 plus 2 times 0, which is going to be 3 power 0 is 1, which is going to be greater than or equal to 1 plus 0, right? That is basically 1 is greater than or equal to 1. 1 is not greater, but 1 is equal to 1. But in either case, we have shown that our basis step is correct. This is true. Now, then what we need to do next is my step number 3. So this in this step number 3, we are going to set up the induction hypothesis, right? Induction hypothesis. What is my induction hypothesis? I will say assume that 3n, okay, whenever we say the induction hypothesis, that means we are going to prove it for n is equal to k value, right? So n is equal to k. So I'm going to prove it for k, which is 3 to the power of k is going to be greater than or equal to 1 plus 2k, that we need to show. And in order to prove this, remember this is an inequality. This has a different way of proving than the equalities that we have seen in the previous examples and the previous videos. So this one is a bit different in terms of algebra. So then if we have done this, now what I have to do, I have to show it, or I have to prove it for, we have to prove it for n is equal to k plus 1. That is our goal. If we are able to prove it for k plus 1, that means now this is correct. Our claim is correct. So how I can do that? So instead of k, I'm going to substitute k plus 1. That means I am now going to have 3 to the power of k plus 1. So remember one thing, as again, let me compare. In the previous examples, we were finding the k plus 1 term by adding the k plus 1th term, right? But here we are going to replace k with k plus 1 only. So this is going to be greater than or equal to 2, this 1 plus 2 k plus 1. That is what we are going to prove, that we have to show. So this means this is going to be 3 to the power of k plus 1 greater than or equal to 1 plus 2k plus 2. That is going to be 3 to the power of k plus 1 is greater than or equal to 2k plus 3. That is what we have to prove. That is what we have to show, right? This is that we need to prove. Then why, how should I do that now? That is another question, that how I'm going to prove that. So I will say to prove it like by assumption or by my by my induction hypothesis, which is this one. This is my assumption, right? Which is this one that we have assumed already. So by assumption, what I am going to get, I'm having 3 to the power of k is greater than or equal to 1 plus 2k. Okay, then what I can do, I have to make it something that we can show that we can prove it, right? So what I'm going to do now is let me multiply both sides with 3 so that I can, because the reason is my goal is I want to reach to the 3 to the power of k plus 1. That is my first goal. So in order to reach to the 3 to the power of k plus 1, I can multiply this 3k with 3. That will make it 3k plus 1. So that's what I'm going to say. I'm going to say multiplying the 3 on the both hand sides. So what does this mean? So I'm going to multiply 3 on both sides. 3 times 3k is going to be greater than or equal to 3 times 1 plus 2k, right? So this will turns out this is basically 3 to the power of 1, nothing else, right? So this is going to give me 3 to the power of k plus 1 greater than or equal to 2. Okay, this is going to give me 3 plus 6k, right? 3 plus 6k, so which is going to be 6k plus 3 if I multiply right hand side with 3. So now what I can assume now is, since I know that this 6k, let me just write it, since 6k is greater than 2k, that is for sure, right? So I can simply replace or substitute 2k, replace 6k with 2k. I can simply do that. Why? Because I know that, let me just write it, replace 6k with 2k. Why? Because I know that 6k is greater than 2k and we are solving a greater than sign, so we can substitute it over here. So in that case, what I'm going to get here is 3 to the power of k plus 1 is greater than or equal to, instead of 6k, I'm going to use 2k plus 3. That is exactly what we are supposed to prove for k plus 1, which is this one, right? So we have prove this inequality. Now, the way of proving is a bit different than what we have been using in our earlier examples, right? Okay, now let's see a few more examples. Let's say I'm going to write one more example here, right? So let's say example 2 for this video. So it says that let's say n factorial is going to be greater than 2 power n for all n values which are greater than or equal to 4. So prove that this is true for all n greater than or equal to 4. Okay, so what we should do, we'll use this our previous knowledge. So step one, what I'm going to say, let p of n is going to be n factorial greater than 2 power n for all n greater than or equal to 4. Okay, then I have to do my step number 2, which is the basis step. And in the basis step, I have to choose the smallest value of n, which is now 4. Right? So that means basis step I'm going to do for n is equal to 4, which is the smallest value of n. So that means it has to be true 4 factorial is greater than 2 power 4, right? If this is true, then we can move forward. This is our very basis step. So 4 factorial is going to be 24, right? 4 times 3 times 2 times 1 is 24, should be greater than 2 to the power of 4, which is 2 times 2 is 4 times 2 is 8 times 2 is 16, right? So which is true, right? So this is true. So we have completed our basis step. Okay, now then if this is true, then we have to go to the step number 3, which is the inductive steps, where we need to set up our induction hypothesis. So I'm going to set my induction hypothesis. I will assume that it is true for n is equal to k. right? For k value. That means I am going to assume that this value, which is k factorial, assume k factorial is going to be greater than 2 power k, right? For all for all k value greater than or equal to 4. So for any random value, arbitrary value k, this is true. If I can do that, that means I have to show that then we need to prove that this is true for k plus 1 value. That means I have to now prove it for n is equal to k plus 1, which means k plus 1 factorial is going to be greater than 2 to the power of k plus 1. That's what does it mean, right? So now we need to show this one. We are going to show, we have to prove this one. If this is true, then only we can say that the whole claim is true. Okay, now how can I do that? Now let's say I can say that by assumption, in my inductive hypothesis, that what we have assumed, what is that? By assumption, it is true that k factorial is greater than 2 to the power of k. That makes sense, right? And then I can what is my goal? My goal is to reach to this point, which is 2 to the power of k plus 1. And here I have 2 power k. So if I multiply it with the 2, uh, uh, if I multiply it with k plus 1, I can do that. So this is one approach, right? I can make it like this one. Another approach is to make the right hand side, the left hand side, this is k plus 1, so make it k plus 1. So this is another approach. So see what we can do and what we can do here. Let's see, for example, what we can do is, let me multiply both sides with k plus 1. So I'm going to multiply, let me just make a note here, the multiply both sides with k plus 1. So if I multiply both sides with k plus 1, it is going to happen k plus 1 times k factorial is going to be greater than k plus 1 times 2 power k, right? So that should be true right now, right? So in this case, what I can assume is, what I can say is, well, k plus 1 into k factorial is nothing but again the k factorial. So it is same, like for example, if you have some number 5 times 4 factorial, right? So this is going to be a 5 factorial, right? This is okay. Let me just write it in terms of plus so that we can see. So we can see, for example, 5 plus 1 times 5 factorial, which is nothing but 6 into 5 factorial. It's again going to be the 5 factorial or the 6 factorial, whatever it is, right? So since we have the arbitrary numbers, this is going to be, this whole is going to become this k factorial once again. And this is true greater than, okay, this is greater than k plus 1 into 2 power k, right? So now I can assume that I can see this. Okay, so this actually is going to be k plus 1 factorial. I messed it. K plus 1 factorial. The reason is, we just have seen that if 5 plus 1 into 5 factorial is going to be 6 times 5 factorial is equal to basically 6 factorial. So the value is the 5 plus 1 factorial. That is why this is 6, the k plus 1 factorial. Okay. And on the right hand side, we have k plus 1 times 2k, right? So since we know that from the assumptions that this k plus 1 is greater than 2, if it is greater than 2, I can substitute 2 in place of the k plus 1. So substitute 2 in place of k plus 1, right? In place of k plus 1. The reason is because this k plus 1 is greater than 2 and we are solving it for greater than sign, so we can do that. So what I'm going to do now is, this is going to be k plus 1 factorial greater than 2 times 2k, right? So that's what we have got now. So this is nothing but 2 power 1. So it is going to be k plus 1 whole factorial is going to be greater than 2 to the power of k plus 1, which is exactly what we were looking looking for here. So but this is what we were looking for, right? So we have proved that using mathematical induction that this is correct. This is correct, right? So n factorial is greater than 2 to the power of n for every value of n which is greater than or equal to 4. So we shall see one last example to prove this inequalities. There are many examples available in the book and in the book exercise. So let's see one more example here. Let's say, for example, we are asked to prove n is less than 2 to the power of n, right? For all n values which are greater than or equal to 1. So we can use the mathematical induction to prove it like we have done earlier. So let's say the step number one is simple. Let P of n is equal to n less than 2 to the power of n, right? This time we are solving it for less than sign. Okay, now the step number 2, which is the basis step. And the basis step, we have to solve it for the smallest value of n, which happens to be the 1 now, right? Okay, so that means we are going to solve it for n is equal to 1, right? So if we add it for solve it for n is equal to 1, that means 1 should be less than 2 to the power of 1, and which is true, right? Which is true. That means our basis step is correct. Now my step number 3, which is inductive step, and where we set up the induction hypothesis. And when we set up the induction hypothesis, we mean that we are going to solve it for n is equal to k for the kth value, right? So that means it should be then assume k is less than 2 to the power of k for all k values which are greater than or equal to 1. Right, that makes sense. And now then we have to prove k plus 1 is going to be less than what? 2 to the power of k plus 1. That now we need to prove. So if we need to prove that, what should we do? Let's see. What we can do is we can simply solve it by our assumptions. So what I can say is, by assumption, by my hypothesis, right, by my assumption that we had the inductive hypothesis, which is k is less than 2 to the power of k for all k values which are greater than or equal to 1. Okay, then if that is true, then what I have to do is my goal is to make the left hand side, which is this k, to k plus 1. That is my goal. Or in other ways, the other goal could be k plus 1 to the k 2 to the power of k to the k plus 1. So this is what I have to do. So what I can do is, how can I make this is, I can say that so we know that our in our hypothesis, what we can see is my k value. Okay, since this value, which is 1 plus k, is smaller than that, so I can add 1 to the both hand sides, right? I'm going to add 1 on. Okay, so I'm saying that 1. Okay, hold on. This is 1 is less than or equal to k, right? Why? Because here is my assumption. It's not exactly the assumption, it is given. So k is greater than or equal to 1. That means 1 is less than or equal to k. So I have to reach to this place in either way, either by using any of the value. So I am using this now to prove it that 1 k is less than or k is greater than or equal to 1. So 1 is less than or equal to k. So if I add k on the both hand sides, what is going to happen? That means if I add k on the both hand sides, it is going to happen 1 plus k is less than or equal to k plus k, right? So that's what we got. So that means what we got is, it is k plus 1 is less than or equal to k plus k. right? So we are able to reach to the one step, which is this one. Now we have to make the other side to the 2 to the power of k plus 1. So we reached k plus 1, and now we reach to the second side, which is k plus 1, 2 to the power of k plus 1. Okay, now one thing that we should note here is we already have another assumption here, right? We already have another assumption here, which is k is smaller than 2 to the power of k. So this is my assumption. So what I can do is that we already have here, right? K is smaller than 2 to the power of k. So my assumption is this one, so that k is smaller than 2 to the power of k, then that means I'm going to solve it for a smaller than sign, right? So I can basically say that I can basically substitute 2 power k instead of k. So what I can do now is, let me say, I can say substitute k 2 power k in place of k, right? In place of k. So what I'm going to get now is I'm going to get k plus 1 is going to less than or equal to, or basically less than. You can assume that okay, so here it is less than, not 1 is less than k, right? 1 is less than k, so it is less than k. So because it is greater than or equal to, but I am going to assume it for less than 1. So k, instead of k here, I'm going to substitute 2 power k. So 2 power k times 2 power k, right? So that means, okay, it is not times, it is plus. It is plus 2. Okay, so let me just do it once again to just show that instead of we were having this result after adding k on both hand sides. So now k plus k, I am going to substitute 2 power k. So 2 power k plus 2 power k. So now it is the fact when you have x plus x, when the bases are same and you are going to have the add them, this is going to be the 2x, right? So that is what we are going to get here. So what I'm going to do here is k plus 1 is less than 2 times 2k, right? So 2 times 2k, which is nothing but k plus 1 is less than 2 to the power of k plus 1. So we reached to this point to prove that this is actually the same, that is we have to prove for k plus 1 value, right? So what we learned in this video lecture is that how to prove inequalities using the mathematical induction, right? In the previous videos, we have seen that how to prove equalities using mathematical induction.